Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Computer Wednesday, we're going to talk about Resistive Random Access Memory or ReRAM. So let's dive deep into it. So what exactly is the problem right now? Problem is that world is hunger for more compute, and primary component of that compute, because be mindful, your CPU or your GPU could be only as fast as the slowest link. Right now RAM is the slow link. We want faster and efficient RAM, because if you keep increasing the amount of RAM, power consumption on servers could go stupid and GPU stupid, meaning it would be just too impossible to cool. So fundamentally we want efficient RAM and we want faster RAM, and there are fundamental core limitation of the technologies that we are using. This is one thing you have to understand. If you understand the core science of something, there is a theoretical limit. All technology, like for example, can you ever make a CRT as energy efficient as OLED? No. Like under known laws of physics, that will simply not happen. That's a physics level system. For example, like if you're burning let's just say oxygen and kerosene, how efficient you can make a rocket engine in vacuum versus oxygen and hydrogen would be always better. Why? Because oxygen is the lightest hydrogen is the lightest element. It will give you higher specific impulse. These are physics level thing. So in computer electronics, there is a physical level thing. Many times we feel like, oh, technology improvement. Trust me, when people figured out how to make silicon based system, they calculated what is the theoretical maximum, and we have not reached it. Like you see Moore's law, but here's still we knew about that. Mathematically we knew. So fundamentally, how we are using RAM, it's super fast, but it's volatile AF. As in, the moment power goes, delete, done, go home. That's why your laptop sleep requires electricity. Otherwise, if you open it up afterwards, it's like, I have no idea who are you. I have to do everything again. So that's there. And NAND is non-volatile, good, but if you compare that NAND technology to this basically floating gate technology to RAM chips, it's like, bro, it's not even in the same league. And again, this is on a fundamental engineering level, how we are building things. It cannot be bypassed. And yeah, you can compare like, okay, 1980s RAM chip to like, 2026 flash chip, but that's cheating. Assuming within the same technological bracket, the output would always be the same. RAM will always be faster. But again, it will always be volatile, and NAND, while it will be slower, it will be non-volatile. And our AI needs bit too much, like faster and faster system. So, but wouldn't it be great if we could store multiple bit per cell of a RAM? We could do that right now with NAND systems, but we can't do that with a RAM system. So I'm gonna go in each tech layer and let's understand things. So tech layer number one, which is RAM. Now RAM is the core of modern systems, and when I say core, I mean fundamentally your CPU's first task is initialize the goddamn RAM. That's why if RAM has an issue, your system does not go. It's like it's off. It's like, dude, I have no idea what's going on. Like if RAM initialization fails, it's like, it would be very difficult for CPU engineers to figure out enough memory or enough compute to work without RAM. Where it's like, even just to throw up an error message, it's like, generally error message comes from your motherboard. If RAM is not working, the blinking light is a RAM. So RAM is core of it, like core. Now, why the heck it's so important? Well, here's the deal. It has super easy access to each cell, meaning each of the bytes, so to say. You can, if CPU wants it, it can go to each bit. Basically, let's just say your computer required a data, right? It puts it on a table. And because it's on a table, it has the luxury of seeing each lines of it. Like think in this way, like you have multiple open pages of multiple books on the table. Table is the RAM. Library is your hard drives or your SSD. So when you are everything is open like that, you can say here. So same thing, which row, which column, tada, that exact bit. I need to change this one bit. CPU can count on RAM to A, find that bit, B, change that bit. All of that will happen seamlessly, reliably, and rapidly. So this is why we can read and write data to RAM very fast, because each bit is accessible. It does not need to take out the whole byte, change it, then put it back in. No, everything happens instantaneously almost. So how the heck we are storing it? Well, if you have an electron microscope, zoom into these puppies, they look like something like that. So what is those blocks? Capacitors. They are holding charge. They are capacitors. Now each benefit of having so much wiring for each cell is that you can address each single cell. Each byte is available. Like generally computer asks for a whole bit, whole byte block rather than each bit. But if it wants to, it can do that. We don't do that anymore. It's like you have enough throughput. And by the way, nowadays CPU itself has multiple level of cache. That's what it has. So fundamentally, and when you are talking about capacitor, when you're making capacitor this tiny, this self-discharge, meaning you have capacitor, cool, you put voltage, that's, let's just say you're on state, great, you're reading it, great, over a few minutes it dissipates. So what do? We keep refreshing it, meaning computer reads it, oh, there is a charge, yes or no, there is charge, keep charging it again. There is no charge, don't charge it. So again, so they want to maintain the state of it. You do not want to rewrite everything on this because of refresh. So refresh has to do two tasks. Not only it has to check every cell, and then it has to reflash everything. And it happens almost every time. That's why the moment power goes away, the end, all of the data in this goes away. Now, to be fair, if you dunk these puppies into liquid nitrogen, the moment you turn the power off, it should last long enough. Some hackers did use that method, liquid nitrogen. It did make it froze enough, and for some reason electron did not leak, and voila, you can read it. So fundamentally, it is power hungry. That's why your laptop sleep state does require power. It is trying to maintain the RAM module, meaning it has to keep charging all of those capacitor fundamentally. And because of so much wiring and the design and the architecture of these puppies, they are fundamentally low density packing, meaning this big of a board will have much smaller capacity compared to your M.2 SSD. So that's on a physical engineering level. Benefit, hyper fast. Each bit is accessible. Each byte is randomly accessible. But penalty, super duper low density and power hungry as hell. Like you might think, oh, RAM, does it really consume that power? Look into servers and you're like, yep, it does. Like bonkers amount of power. Now we come to NAND. Now NAND is non-volatile, that's the great part. You can turn it on or off, it does not care, it will store the memory. It's what we call SSD. But it's where the heck it's storing charge? It's storing charge like a capacitor, but not in a capacitor. It's storing it in gates. Basically, if you know MOSFET, something similar to that. So there is floating gate, and it's in that gate, it's charged. It's like so if the gate is empty, like inside the gate there is no charge, that's 0. And it can put charge into it, that's 1. So it can store that. And based on your system, so to say, how much charge is there, you can read out whether it's 0 or off. Now be mindful, people figured out very early on, it's like, hey, why only have on or off? What if you have multiple levels on it? So you could do that. That's what we call multi-level cell, triple level cell, or quad level cell. So if you have nothing, like nothing, 0, shunya, that's 1, 1. If you have some, that's 1, 0. If you have a bit more, that's 0, 1. If you have a lot more, that's 0, 0. Now you're like, wait a minute, that would require a very sensitive circuit. Yes, that's why NAND chips on principle can work at very high voltage. Like internal voltage could be as high as like 10, 20 volts. Like, wait a minute, why? Well, the higher the voltage, the easier and cleaner the signal becomes. If you try to distinguish each levels inside 1 volt, yeah, noise, background noise alone will make it very difficult. So that is the fundamental limitation. So, and to increase the packing efficiency, all of this is in shared bus. You see, each is a P channel and each of them are N channel. This is how it's physically constructed. So you can't access each one of the nodes specifically for write operation. Read operation you can manage. If you want to do a read operation that where it almost behaves like RAM, it's almost to do it. Almost. Not as fast, but almost. But write, yeah, it has to flush the whole thing and then write it. And there lies the core problem. That's why write operations on SSD is always slower than the read speed. It could only be compensated by one way. You over provision it so much that bus becomes the limitation. For example, it's very easy to do nowadays with SATA 3 interface. Like you have a SATA SSD, it can be made so fast that write speed is higher than let's just say 600, 650. Your SATA controller can't do faster than that. So it's like, bro, it's saturated. On theoretical read would be like 1200, but here's the link speed is 600. So write speed will always be slower because it has to take all of the data, put it into a RAM. That's why your SSD has a RAM. Put all of data into the RAM, flush this whole thing, rewrite with a new data change again. And there lies the core problem. So, and because you are dealing with charge, not a capacitor, and again, it could have multiple levels, it requires time to stabilize. Fundamentally, on a physics level, all the analog to digital converter that's actually doing the measuring is like, yes, no. It's not like, It's not as fast as RAM. It fundamentally requires charge to travel, to equalize, to stabilize. Otherwise, it will not work. Now, it's getting faster, but physics limitation. It will never reach the speed of RAM. Like, it's on an electron level. You can't do too much to it. It's too slow for RAM use and too leaky for long-term data archive. Even though it's non-volatile, it's not classified as long-term archivable. Meaning, if you are a corporation, you will not store your tax record of 10 years into this. You will store it on a magnetic tape and hope you keep replacing it regularly. So fundamentally, it does work. And as we have improved the technology, we have two choices. For example, if you are running mission critical system, you will buy single level. Why? The voltage would be huge, as in like, oh, if it's 2.5 volt, it's on. If it's anything above 1.4 volt, it's still on. Anything below that is zero. So that's your gradient, and you have room. So even a degraded cell still works. And they're like, okay, there is no moving part. What's the degradation? Yeah, that electron barrier, the basically dielectric you have, you're forcing electron through it and pulling it out. Every read and write operation. Read does not do damage to it, write does. So every time you're writing to it, you are eroding it. And as in like, take this chip fresh out of the factory, slice it, put it in electron microscope, the dielectric layer would be like GG, pristine, strong. Use it like for 3-4 years in a heavy compute environment, it will be destroyed. So it's a physical wear item. Let that be very clear. It's physically wear. That's another aspect of it. RAM will work for decades. This will not. Physically, it will not. That electron layer will be like, bro, I don't. Okay. And again, to compensate for that degradation, either A, have large enough voltage range like single level cell, whereas like, bro, I have so much wiggle room that sloppiness of that layer will not compromise too much. But you want high data package, you could have quad layer, which translates to 16 voltage levels. Yeah, that's why quad layers are not used for mission critical things. It's great for packing, meaning your micro SD card could be 2 terabytes, but not great for longevity, meaning you should not trust that puppy for long term, because any failure would be such a big failure that it will corrupt large segments in one go. That's why like servers will, if it's mission critical, it's a single level. Like they're not even talking about anything else. It better be a single level. So too slow for RAM, too leaky for long-term data archive. So meaning even if the barrier layer is not degraded, it's still a kind of charge electron kind of stuff. It will slowly leak through. Not in 1 year, let that be very clear. But people do expect like 5 to 10 years, bit rot should start to happen. 10, 20 years, good luck. So there is fundamental, it's a good thing. Off, it works when it's off, great. It has very high packing density, great. It allows you to have each cell have multiple state store, that's great, but does have some wear limitation. And again, this is another thing, if you use SSD as a RAM, even for your old computer, even though speed will match, you will find that it will not last very long. It will degrade. And again, people are like, when they used a micro SD card for Raspberry Pi as an operating system disk, it used to wear down very quickly. They were TLC. Basically, micro SD cards, they are not classified as high priority, so rarely they are single level. So they degrade very quickly. Now we come to the ReRAM. Now you must have understood all the concepts of the previous one. Then it's just that, what if you have a cell, instead of storing charge, what if you are storing a resistor? It's like, wait a minute, what? Yeah. What if it's a stuff? It's almost like a potentiometer and you're setting its state. So it's much faster to read compared to NAND, simply because it's much quicker to read a resistor than it is to like, okay, how much charge is there? And again, because you are talking about gates, you are talking about floating coulombs and all that, you do need some time to equilibrate. That's on a fundamental physics electron level. Here is like super fast. And resistance are long-term stable. There is no energy into the system. So it is like, bro, I'm set. Like if you set it to low resistance state, it will remain low energy state. There is nothing to leak out. Once you change it, it's like there. And if you want to rewrite it, you increase it with a voltage shock, so to say. So resistance is long-term archivable. Again, this is theoretical at this point in time, that it could work for 20, 30 years without bit rot. That's hope. And again, on principle, it should happen because, our NAND chip does store memory. It's just not great at it, but does store memory. So this should be exponentially better because there is no high energy state that wants to leak out. It's once you change it, it's stabilized. And it can have multiple state per cell. Each cell could be like, hey, low resistance state, high resistance stage 1, high resistance stage 2, high resistance number 3. So each of them could have multiple gradient. And be mindful, the gradient, how do you measure the gradient? With a resistor meter. So it could go from like, 1 mega ohm. That would be like, fully open. That would be 1 mega ohm. And then you can keep dropping it down to 10 kilo ohm. That's a lot of room. That's like going from here to here. That's a lot of room. And meaning, in principle, I can see that one cell could even go up to 256 levels and should be able to store 1 byte. Each cell, if it can store 1 byte of data, that's like, shut up, take money. That's like, you have no idea what level of technology we are talking about if that can be attained. And going from 10 kilo ohm to 1 mega ohm, you have enough room where you can slice each of them with enough margin that there will not be noise in the system. So that's the exciting part for people. People are like, bro, we're going to start with obviously on and off just to test everything and validate, but quickly switch to 16, 17, 14 states day one. Like, that's everybody who's working on it is like, yeah, we're going to do that. It's like, we're not even trying to make RAM like RAM. We are making something that will be from day one, much higher density than RAM, and very quickly, like 2-3 iterations afterwards, it will be like your SSD on your RAM stick. So, and each cell is addressable. The geometry, the designing, the engineering is done in such a way that it acts like a RAM. Basically, rows and columns are fully accessible. It's not like whole blockade. So you have that. And it does not require refreshing like a capacitor does. Capacitor requires recharging. This is like, bro, once you set it, forget it. Meaning, once you close your laptop, let's assume the battery forgot. Like, you lost your battery. It was completely discharged to 1 month, and then you plug it again. You open it up. It's like, bro, I got you. Your mouse pointer was here, it will be here if you have set it in that way. So fundamentally, and how do you construct it? It's electrode and a bottom electrode, and you have metal oxide with a conductive filament. Now this filament is the black magic of it. It's basically electron mobility kind of thing happening. Again, it's like whole pairs and all that. So that's why it's changing resistance. It's not changing like, oh, it's now a cell, it gives you voltage. No, it's just changing the resistance. And to read it, again, resistor, whenever you have multimeter and you're trying to read it, it generally sends some current through, some amount of voltage through probes. So again, if you are using the probes, how the heck you gonna make sure that you are not damaging it or changing it? Well, for reading the value, you're gonna use low volt, as in like give or take 500 millivolts. For writing it, you could be as high as 5 volts. So writing is a very strong process, and reading is a very low energy process. So this actually has an advantage that if you want certain sections to be not overwritten, it saves energy. It's almost like OLED, where black is off. Is the same thing here. It's like, hey, I don't have to spend energy here simply because reading it, I can read it at 500 millivolts. I don't even need to spool up my DC converter and pump up to 5 volts. So that's the whole point. Top electrode, bottom electrode. Now, I cannot talk about the chemistry here simply because A, I don't understand it. B, it's not sorted. Every research paper I'm going through is different. Some is like, titanium oxide is the one thing that I can almost guarantee that somebody will bring out. Unless we find something better, somebody's going to bring out titanium oxide system. This whole system. So this is the ReRAM. Each cell, basically the structure is designed in such a way that it's a RAM. The packing efficiency is much higher. It does not require refresh, and reading it is a very low energy process, and it can retain its state even when it's off. And on paper, on principle, this puppy should outlast a NAND flash chips in terms of memory storage in long term. So what can we expect in the future? Now here's the this could be the thing, as in this is what we classify as paradigm shift. Like if you studied computers in 1980s, specifically 70 period, like we barely had 4-bit computer at the starting of 70, and the end of 70s, we ended up with Intel x86, so to say. So that was paradigm shift. This has the potential of that paradigm shift, because if done correctly, if what people are expecting can be done, let's just imagine a world where from engineering point, they can't pack, like again, they can't pack too many compared to a NAND chip. So they can't beat a NAND chip in that. But because they have resistance and they have the luxury of having so much dynamic range in the resistor, what if each cell is a whole byte? It's like, yeah, you can access it, but it's the whole goddamn byte. So that on paper could create a system where you do not need any SSD or RAM. You just have ReRAMs, the end. It is the memory, the end. Computer will behave as in like whole of its operating system is in the goddamn RAM. Like there is no slow storage, there is no fast storage. So that's from a paradigm shift point of view. Second, why people are pouring so much money into it right now is that it can act like an analog computer. For example, whenever you hear about AI, what is AI? Mostly it's a neural network nodes. What is that node? You send a one data, multiple nodes work on it, and you have output. Here's the deal, you can do that with resistors. Again, those who work in analog domain, it's Wednesday for them, but for digital people, it's like, what? So imagine you sent 5 volts. Okay, how much voltage should be on the other output end? That can be defined by the resistors. So you have multiple resistors, right? Each node have multiple vectors, so to say. All those are arranged in series. So the collection current will tell you what happened. Like I sent this data, it goes through this much. What is the output? RAM is acting like a computer. So you can do AI summing operation on a hardware level, fundamental hardware level. Although let me be very clear, all the engineers who are working on it, they are very clear. This is not for training data. This will not work for training. It assumes you know the training, like you know the weights and values. Then you want to project that weights and value into these hardware, and this hardware will be like exponentially fast, meaning you will take a data center to train it, and that final AI could run into something like this without consuming energy. And you will not be like, oh, it's a bit slow, compromise. No, it will be as fast. Again, assuming the training went well, training to this projection can be done in such a way that it's like, bro, I got this. It could take megawatts of power to train AI, and it could take microwatts of power to run it on a hardware level. It's a hardware domain thing. So that's a very interesting. That's why people are pouring money into it. And they have like hafnium, tantalum, zirconium, this and that. It's like, that's the only thing I know is titanium oxide. But again, some people are also working with lead, but you get the point. So it does need time to cook. If you try to look into its source material, some of them are ancient, like not old, they're ancient. So it does need time to cook. And again, we do not know for certain whether this will become the thing in the future or not. It could, or it may not. So this was my presentation on basically ReRAM. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you enjoyed it, please click the hype button. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me access permit. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free. And as always, thanks for watching.